Hey everyone, and welcome to Mr. V's Literally Just Airplanes. I thank you guys for all following my Anchor.fm page. I am starting something new, starting today. This is a test. I haven't done it in a while, but I'm going to be doing video stuff. So all about airplanes, just for the video stuff. I'm going to be discussing some 40-13 stuff today, and some inspection stuff. So basically anything non-destructive I'm going to be talking about today. And it's something new for me. The material's not new, but just the video stuff's new for me. So bear with me here. If it's bad, I'm sorry. I will get used to it. Alright, let's start. So last week I talked about airport operations with tugs. And the tug stuff is really interesting because it's not just airplanes, it's the machines that pull and work around the airplanes. On the cargo ramps, on the airline ramps, just basically everything. So when it comes to like inspecting and maintenance stuff, that's really what goes behind the bulk of the aviation work. So when it comes to non-destructive inspection, it's very important to inspect things of the aircraft that we cannot see with our eyes. So I have the 4013 here, the Bible, and I'm going to discuss some non-destructive inspection terms today, including visual inspection, eddy current inspection, magnetic particle inspection, penetrant inspection, radiography inspection, such as X-ray, ultrasonic inspection, tap, acoustic, thermography, holography, and shearography. I'm not going to really touch on a lot of the last four as deeply because I'm not really aware of the last four as much. Since I'm still in school, I'm still learning a lot about them. But from last semester with NDT stuff, I think this is going to be very interesting because it's new to me, but it's also very cool. So let's get started. So we are going to start with going to page 5, chapter 5, non-destructive. So let's go to chapter 5. And when I got this book, it was very, I didn't think I was going to be using it as much as I have, but let me tell you, I've been using it every single class I've had, and it has benefited me every single time. So bear with me here. All right. So I'm not going to go over the general stuff because most of you should know what NDT is. If you guys do not, NDT stands for non-destructive testing, or NDI is non-destructive inspection. So this is something you do if you have any type of cracks or damage or any type of stuff that you cannot see in the airframe or engine per se. So like an example would be, I have a wing and it has a crack through the entire part of the wing. You would use something called non-destructive testing or inspection to test it to see if there's any problems with it. So the FAA has made a chapter in this book, the AC 4013, that discusses procedures and all the levels of non-destructive testing. So you have level 1, level 2, level 3. And to approve these procedures, it goes through part 43. So I'm not going to go over part 43. That will all be for some other time with all the airworthiness directives and the procedures as well. But I'm going to go over the NDT levels. So after referencing the Air Transport Association specification 105 guidelines for training and qualifying, the non-destructive methods come for level 1 special, level 1 and level 2, level 3, and training qualifications. Level 1 is basically getting to know the material in class. So like, for instance, like you'd be doing book work, you'd be doing stuff inside class, doing things that are in a classroom manner and a book manner per se. So like PowerPoints or slides. So the individual must be able to pass a vision and color perception examination, a general exam dealing with standards and NDT procedures, of course, and a practical exam conducted by level 1 or conducted by level 2 or level 3 certified persons. So basically, it's like any type of practical test you're going to take, especially like the airframe and practical test, where basically you're going to be doing things with an examiner next to you. So it's basically like that. You're going to have an examiner basically show you the ropes and get to know things on a daily basis there. So level 1 and level 2, so level 1 special is mainly the classroom stuff. Level 1 and level 2 is The individual shall have an airframe and power plant mechanics certification and complete the required number of formal classroom hours and complete an examination. So basically, if you have your A&P and have a certain amount of hours on your required class time for level 1 special, you're good to go. Level 3. So there's also, I'm pretty sure there's 3 parts to this. The individual must have graduated from a 4-year college or university with a degree in engineering or science, plus 1 year of minimum experience in NDT and an assignment comparable to that of level 2 in applicable NDT methods. So basically, you might have your A&P, but if you do not have you don't have a bachelor's degree in science or engineering, you cannot be a level 3 certified NDT personnel. You can only be a level 1 or level 2. So basically, the part 2 is the individual must have 2 years of engineering or science study at university, college, or technical school, plus 2 years of experience as a level 2 in the applicable NDT field. So basically, you have to have experience as a level 2 NDT as well. The individual must have 4 years of experience working as a level 2 in the applicable NDT methods and complete an examination when ready for it. The training qualification certification, part chapter 5.4, is basically getting used to the materials itself. So first you have the NDI methods, and it goes over all the different types: eddy current, X-ray, ultrasonic, and those 3 must be tested by the FA all the time. So for instance, if you do not have a certain qualification on something, it's not going to really affect it per se. And you have to have an ATA spec 105 on those 3 to be able to do it. Now, of course, everything's going to have flaws. Of course, NDT, NDI is going to have flaws. It's kind of hard to pinpoint each flaw unless you have any experience on it. So like one flaw is, although a specific discussion of flaws and processes will not be given in this AC, the importance of the area should not be minimized. Inspection personnel should have known where their flaws occur and can be expected. So misinterpreting, of course, that's when you try to find someone else to help you out or a supervisor to actually look it over with you. All NDI personnel should be familiar with the detection of flaws such as corrosion, inherent flaws, primary processing flaws, secondary processing or finishing flaws, and in-service flaws. The following paragraphs classify the discussion types of flaws and anomalies that can occur in these. So when I was in AMS 115, when I was in AMS 117, we went over NDT testing, and we did eddy current testing. So in eddy current testing, you use a electric current to go through it. Magnetic particle, you use a magnet to use it. And ultrasonic, you use an ultrasonic wave detector to use that. All of them have different methods. Each of them can find different flaws. Some of them can find the same flaws, but some of them are pinpointed to find their own type of flaw. Corrosion, electrochemical, that's a big one. Inherent is type of molten state, or the state of the material itself, the state, the liquid, the solid, the gas. That's basically the inherent flaw. Blowholes are a big thing on pipes. That's one of them. Pipe shrinkage, that's another form of it. Segregation, or the non-uniform of the material, being able to split apart, that's another one of those. Porosity in the holes is another big one. Inclusions are impurities, such as like slag, oxides, sulfides. Basically, any type of deoxidizing material is going to be noticed on that as well. And then, of course, shrinkage cracks, the smaller part of the corrosion aspects caused by stresses and when it cools and solidifies. So those are the basic flaws when it comes to that. Then there's different categories of flaws. There's the primary processing flaws, which are seams, laminations, cupping, cooling cracks, flakes, forging laps, forging bursts, hot tears, and cold shuts. There's a whole nother side of 17 of these, including incomplete welds, weld undercutting, cracks in a weld crater cracks, cracks in the weld heat, a slag, and a scale of oxide formed by the weld itself. The secondary processing or finishing flaws. Now the secondary is different because it includes the flaws as associated with the various finishing operations, so it depends on the type of operations that is finished with it as well. So the flaws may be introduced by heat treating, grinding, and similar processes in that aspect. So when it comes to like descriptions and basically a description of secondary flaws, just think of like after the weld or casting or forging. That's really the secondary stuff. Now, I know it's kind of confusing because weld craters and cracks in the weld from heat are technically primary. The secondary is from after doing something to it other than welding, so like forging and casting. In-service flaws. Now, these are the ones that you really should notice the most. This should be something that is automatically there when you visually look at it. So, like, we have stress corrosion cracks. These can develop on surface parts that are under tension, stress, and service, and are also exposed to corrosive environments. So, basically, wheel wells, underbellies of fuselages, a bunch of other areas that you can think of that are basically in contact with the ground or air, because oxide is in the entire Earth's atmosphere no matter what. You're not going to run away from it. You're going to see it everywhere, especially when you're over the ocean. The salt's going to come up into the airplane. Overstress, that's a big one, especially on the wings with the struts, the longerons, even the engine mounts, the nano mounts. That's going to take a lot of stretching when it bounces up and down, and you're going to see start bubbling and filiform on the sides. Fatigue cracks are also similar to overstress. Of course, you're going to have fatigue for longer periods of time. So, like, if your wing bounces, if your fuselage expands, contracts over time, it's going to put some crack and tension on the fuselage. Unbonds, disbonds are basically adhesive. So, basically, adhesive flaws. So, you're going to have seams. You're going to have some of the enamel that's inside of the fuselage. You're going to have the pro-enamel, that's going to be the seams, and the sealant, that's going to be inside the fuselage of the wings. Fuel sealant, a bunch of other sealant adhesive stuff, that's very important to know as well. Delamination is the last one. Ultrasonic is the primary method to detect this because of the composite structures that have to deal with delamination. So, going over all the processes and flaws, just remember that there's always going to be so many flaws that you're not going to be remembering off the top of your head. That's why a lot of mechanics have this book or the app in their toolbox for ready to use. A lot of them actually have it on their phones. When I worked at Textron, they literally just pull their phone out, open it up, and it's right there. They download it and notice it. A lot of them, like I would do, and a lot of the engine mechanics, is they would print out the actual forms, not the book. They'd print out the forms and actually look at it while they're working on, like, brakes or some other stuff to actually inspect it. A lot of the times the NDT inspectors will actually come to the hangar and they'll actually hire a company to do it instead of the mechanics to do it. Even though the mechanics can technically do it, most of them can once they get certified through the FAA. So when you're looking at the NDI method, you need to know some things. You need to know the material, you need to know the size, the shape, the weight, and the type of defect you're looking for. Because if you don't know those things, you're not really inspecting, you're just kind of looking at the airplane. It's basically looking at this computer and not knowing each part of the computer and not knowing where problems are going to be at. So, like, if there's a crack in the monitor and I didn't know what a crack in the monitor was, I'm just looking at the screen blankly. So it's the same thing with airplanes. You need to know what you're looking at, because if you don't know what you're looking at, you're not really going to know how to fix it. So we're going to look at all the different types of inspections. So basically anything you're going to be looking at through your eye, you're going to be looking at things with inspections. So visual inspections. So the visual inspection, there's a lot of advantages to visual inspection. We're going to go over that when we do each title of inspection, but we're going to go over the types of inspections first. So the first type of inspection is visual inspection, like I just stated, magnetic particle, penetrant inspection, eddy current inspection, radiography inspection, ultrasonic inspection, acoustic emission inspection, thermography, holography, shearography, and tap testing. Now, there are more types of inspections, but they're all categorized into these. So really, those are the ones you really need to know. So I'm going to go over it again. Visual, magnetic, penetrant, eddy current, radiography, ultrasonic, acoustic emission, holography, shearography, and tap testing. All of these are going to have disadvantages and advantages, but I want you to determine which one is the best for the material it's working on, especially when you're going out there and working on aircraft, especially when a customer comes in with an aircraft that's been sitting for a while and you need to determine how much it's going to cost them or even just get a new airplane and scrap this one. So I'm going to go over the advantages first before we go into in-depth with each one. Visual inspection is always a must-do. It doesn't matter what you need to do. A visual inspection is because you're looking at it. You're not going to be able to not do it, because if you're working at an airplane with your eyes closed, you're not working on it. You're literally just have your eyes closed, so there's no point. So visual inspection, the advantages are it's inexpensive because it's your eyes. I mean, you're not paying anything. It's highly portable. It's immediate results off the top of your hand, unless it's something inside you need materials with. Minimum training and minimum part preparation. Yes, it's perfect for that. Especially when you just want to get something done quick. I wouldn't say quick. Get it done in a timely manner, accurately, while your supervisor checks it out with you. It's better to have more than two eyes, because then someone else can use a different perspective on that. The disadvantages, though, is the surface discontinuities only. So basically anything on the surface, that's what you can see. If it's inside the surface in the material, you're not going to be able to see it with your naked eye. So that's when you need some more materials. It's generally only on large discontinuities. So basically, if I'm looking at a wall in a certain spot of the wall, then I can look at each part of the wall. But if it's big enough that you cannot look at the entire thing by yourself, it kind of is time consuming. And then this is one thing that I do like about this book putting is misinterpretation of scratches. So I've noticed that when you're looking at scratches, sometimes they can be buffed out, sometimes they can be wiped off, and sometimes they're not going to come off, especially when it comes to piping, especially with brake lines, hydraulic lines, fuel lines. They can have a certain amount of percentage of scratches on them. So when you have an angle like this and a certain amount of scratches on each part, you have to match the percentages. But if it's after that percentages, you're going to have to start using your inspection methods to be able to be like, okay, that's not going to work for me, especially on hydraulic and fuel lines, because they're main parts of the airplane. The next one is going to be dye penetrant. It's portable, it's inexpensive, it's sensitive to very small areas, and 30 minutes or less to accomplish. So it's not as time consuming, and it's minimum skill required. But the thing with dye penetrant is it only locates surface defects. So it doesn't locate subsurface defects. So like interior parts of walls with the 2x4s in it, or nails inside of it, or even piping inside of it, you're not going to be able to really look at it. With the airplane, you can look at the wing, you can put stuff on the wing, or even the engine parts, but you cannot see inside of it. It definitely works very well on engine parts. So like in our tools class and our NDT class, we learned how to use that on crankshafts and camshafts to see where the blemishes came off of, so you can see where the scratches are at. If you can't see them, use dye penetrant, and the dye penetrant will actually use a black light over it, and it'll actually show it. It'll actually sit in that crevice or crack and pull out with the black light. So it's really cool. It's rough or porous, and a high degree of cleanliness is required. Yes, it does need a lot to clean. The magnetic particle is very nice because it can be portable. It's also inexpensive, and it's really fast. The issue with that is the surface must be accessible, and the part preparation is required. Removal of finishes and sealant on it, because if you put a magnetic particle inspecting test particle and personnel on it, it's literally just, if it's wet, it's not going to stick to it. If it's a certain type of material that's not magnetic, which is not ferrous, it's just going to bounce off. It's not going to stick. If it's ferrous, it's going to stick, and you'll actually be able to actually use it. So if you're not using the right material, there you go. You can't use it. And the part has to be demagnetized first. Let me stress that again. It has to be demagnetized, because if it's not demagnetized, it's not going to get a good reading off. Number 3 is eddy current. And eddy current is also very portable. It can detect many different types of variables. So this is why I like eddy current a lot, because it's immediate results, and it's sensitive to small areas, and it's thickness sensitive. So if you have something that's really thick, so for instance, if you have a strut, and now a strut you might think it's not really thick, but the strut mounts, or the strut caps on the bottom part of the strut, they actually hold the actual strut and its main body on it. That's pretty thick metal right there. So if you can't really get into it, you can see it, but you're not gonna be able to detect it. And that's where eddy current is perfect at. It's also great on solid parts or flight controls, such as a elevator or a horizontal stabilizer, even a rudder or a vertical stabilizer, because it can detect through it with not as much hollow. It's a hollow area, so it can detect through it immediately. The disadvantage of that, though, of course, it's time consuming for larger areas, yes. Excuse me. It's skill and training required, yes, that, of course, that's going to be for everything. And it's only for electrically conductive materials, yes. Eddy current is going to deal with materials that are conductive. Now, if you don't have any, if you have like an insulation or foam or something, it's not going to work like that. But if you're using this on different type and non-conductive materials, then you should know the difference between visual and that. So that's when you wouldn't do that. And I don't even know why you'd inspect seats or anything like that with that type of material. That should be a visual inspection. The mounts, on the other hand, now that can be used with eddy current inspection. Ultrasonic inspection is another key one because it's got no radiation hazard. That's a good one. All I'm going to say is after ultrasonic with X-ray and isotope, it's going to get more expensive and time consuming because of the materials that are needed. But ultrasonic is another great one. It uses rough surfaces as an interference as a negative because it's used for smaller and smoother surfaces. This one is great because it's a wide range of materials and thickness can be inspected. So literally anything from maybe 0.025 to 0.25 to even bigger up to an inch, that can be measured from that. And these things, it can measure anything from mounts to lines to slats to flaps, anything solid enough to actually go through it. The ultrasonic can do that. An ultrasound, when you're looking for a baby, you're gonna put on the woman's stomach, and the woman's stomach it's gonna go through it, and it's gonna detect the baby. It's gonna bounce off the baby, and that's where the ultrasound comes back. It's gonna use the frequency and the waves to bounce back to the actual machine. That's how the same thing's gonna go with an airplane. Of course, ultrasonic, high degree of skill is required, and it's highly sensitive to sound. Okay, I guess that's a pretty bad thing, especially in the airline industry and aircraft industry, because there's airplanes that are loud. But it's still a great way to inspect machines and particles. Now, the X-ray is a different ballgame because you're using radiation. And this permanent test record is obtained. So once you do it, it is obtained and it's over with. So now that can be a flaw as itself because it's a safety hazard. Because if you do it with a lot of people around, you're going to have to tell them to leave because this is something that you do once. It's very expensive and it's slow. It probably takes up to 8 hours just to set this up. Sometimes even 6-7 hours at a time while people are working. And you don't want people around this X-ray stuff because it's radiation. Because of that, it's highly directional and sensitive to flaw. So basically, any type of sensitive motion inside, it's going to mess everything up. You have to restart everything. That's why X-ray is not really looked at. Now, isotope is a little bit similar to X-ray, except it's portable, it's less expensive, and it can inspect the hidden areas. Now, this is good for the hidden areas because it automatically detects it. But the thing with isotope is you have to get it confirmed by federal and state regulations, which can take a little bit, especially if the state itself does not like that type of radiation practice. So after going over all the advantages and disadvantages of NDI methods, I'm not going to go too in-depth with each category. I'm just going to state off since I already went over the main things about them, I'm going to state off just some sentences of it, so just to summarize each part. So, visual inspection. Your eyes, that's main one, because actually, visual inspection can also be with your sight and your hearing, because other than your sight and your smell, your hearing can actually hear the issues. If you can hear the issues, that is technically inspecting it because you listen to things that are wrong. You might not know what's wrong, but you hear it. Same with the smell. If you can smell burning fuel, burning oil, burning coolant, or burning hydraulics, you know something's wrong because you can smell it. So that's something that's not really mentioned on here, but it's definitely an inspection method. One main thing with inspecting as well is you can use a flashlight, of course. A lot of people in the aircraft industry, in the diesel industry, they use LED flashlights and head mounts because they don't have to use their hands. And it's brighter. It uses more clarity to detect the issue. Magnifiers, borescopes, and optical designers are another way to detect visually. Inspecting the inspecting area is, it's described in this book with a bunch of different descriptions. So like, you have to use the way you look at it, blah blah blah. If you see an issue, say something and write it down in your logbook. If you see it, fix it. So with the inspection itself and visual inspection, we go off to the next one, which is eddy current inspection. The eddy current inspection, like I said before, detects surface cracks, pits, subsurface cracks, corrosion on inner surfaces, and to determine alloy and heat treat conditions. So this is great when trying to determine a magnetic field around the material. So it uses coils and probes, and it uses to induce service-induced cracks. Now, I have a picture of this because it's easy to explain, but it's nicer with a picture. So if you look at this, you see the balance points of the actual material. So once the balance points are used in material, the actual readings will come back. Now once the readings actually come back, it's easier to determine what's wrong with it. So like the thickness, the balance point, the crack response. If it's somewhere in the middle, there's a crack. If it's somewhere on the outside or even close to the outside, there's still a crack because it's not fully off to the side. Now, if the crack is deep enough where it's noticeable, of course, you're using visual inspection. But when it's eddy current, you can actually detect the thickness, and if the thickness gets smaller, bigger and bigger on the edge of it, you know there's something wrong. If it starts getting closer like this on the bend point, and it's literally almost touching, and it's kind of building off, there's crack response on the liftoff area. So the balance point crack response, kind of like a circular picture, and the liftoff area on aluminum, on a surface crack, is going to be like this. So let me go over that again. So the aluminum surface crack, the response from the balance point is going to go like this. So you're going to have it go literally like in a loop, two parallel lines together, and once you're at the end, it pulls off and makes a circle. That's signifying that there's a crack on the surface. Subsurface, you're going to go all the way to the balance point side, and once you're on the balance point side, it's going to show a loop. And once the loop goes on that side, you have a crack in the subsurface. Now, sometimes there's going to be letters. You're going to have A, B, C. So if the A is on all the way, it's going to have a little tiny little crevice there. B is going to have a little bit of a bigger crevice, and C is going to have a bigger crevice. That's going to decide the thickness of the crack. So if the balance point is just a little bit, it's going to be not as big. But if the C goes all the way up to the liftoff point, you know it's a big crack. And that's when you're going to have to replace the material part. That's another reason why I like eddy current, because it comes back immediately. So if you go over it a couple times, it might read it immediately off the top instead of going over it 4 or 5 times and trying to get one accurate answer. So once you actually get that accurate answer, it will, like I said earlier, it will loop around. The bigger the actual response, the bigger the crack is. The smaller the response, the smaller the crack is. Now, corrosion inspection is, like I said earlier, a big deal with this as well, because corrosion is one of the main factors of aviation fatalities and accidents. So when you're going over corrosion, you're going to have to use a shielded probe with a coil diameter about 0.15 and about ½ an inch. Once you can get to lower frequencies, the actual frequencies will bounce a lot faster, instead of using higher frequencies, which will go higher and longer. Because you can have a deeper material and use it, and have a higher frequency, it will not reach it. It will actually reach it faster because it's trying to get down, but the lower frequencies will literally hit it immediately and be done right there and then. So that's one of the reasons why I like eddy current. Now, when we go to magnetic particle, this is where things get a little bit more interesting, because they're held in by another type of magnetic field that is used with the black light. Now, I'm going to show you this picture again for magnetic particle, but if you actually have it here, where my finger's at, you can have the different types of cracks, the skins, and all that. The book goes really in depth with it, and it's kind of hard to describe it because these are kind of older pictures and they're all doodles. Now, when you're looking at a crack, you can only see the actual top part of it. So, for instance, if I had a book, if I'm looking at the book from this angle, see, now you guys can see it from this angle because the camera was on this angle, but I can only see it from this side. So now what the magnetic particle inspection is, the black light will come in and the particles will shoot out in the different directions instead of having one direction. which is really cool because then you can actually see it and actually be determined that way. Now, magnetic particle inspection is a method for detecting cracks, laps, seams, voids, pits, subsurface holes, and other surface or slightly subsurface discontinuities. So, but now it's used in ferromagnetic particles. It's only ferrous materials. Usually use it for final inspections and receiving inspections because it's the first thing you do immediately. So now, there are different types of test methods for magnetic particle. There are so many different specs on here that I do not want to go over because it's dry and it's boring. Anyways, the number of standards, each of them have a different test ratio on it. They have the non-fluorescent and they have fluorescence. Now the magnetic equipment itself is small, it's inexpensive, and it's permanent magnets that are very strong, but sometimes not as big, which is nice because then they can be portable too. Actual current flow through a complex part may be reduced as much as 20% by the resistance load of the rated input instead of waiting as long as for the other part of the input. That is another nice thing, because if you start actually using the current flow in a smaller resistance part, it's going to be harder to find the actual problem. So preparation of the surface, this is another big thing, because if you do not prep it right, you're not going to get the right actual material, and you're not going to get the right reading. So removing the protective coatings on it. The part should be free of grease, oil, and rust, so you can actually, it can sit instead of just slide off and not read it correctly, because if you have grease over it, it's not going to read it, and one, it's going to get messy all over your materials. Of course, exercise extreme care to prevent any cleaning material and magnetic particles from becoming entrapped, because if it gets entrapped, then it's going to expand over time. Because we know airplanes, temperatures, the colder temperature contracts, hotter temperature expands. If you put something in a crack, it's going to expand and contract because it's sitting there and the pressure is going to want to go out. So make sure you do not put any materials in there when you go over the test. Make sure there's no water. Make sure the magnetic particle examination is used correctly. And the methods of examination, there's 3 different types of methods. There's a wet continuous method, which basically means you're applying 2 shots of magnetizing current for half a second. So like wet suspensions of fluorescent particles. You're using water or oil with that. So that's where the wet stuff comes in. So that's where the wet continuous method comes in. Now the dry continuous method, this method is not recommended for use on aerospace components because of its lower sensitivity level. So like I said, the dry is, I would say, safer for the material itself, but you're not going to get as many readings off the top of your head, and it's going to be not as accurate. Now, the residual magnetization method, this method is used for the magnetization that's used off of it. So it's going to be the stuff that's just left out. So this method is dependent upon the retentiveness of the part. So the strength of the applied field, the direction, magnetization, and the shape of the part itself. So that's where that comes in the handy too. So the magnetic particle has, of course, in electricity, you're going to have the coil shot, the yoke, and the cable wrap with it itself. And I can go way more in depth with that, but I'm only going over the actual materials and the actual methods to do it. There are so many different methods to do it that this book itself has every single method to learn from it. So the next method after this is going to be the penetrant inspection. So this is going to be like a dye penetrant or any type of penetrant. So it's kind of like inspecting in an AC system. So when you put liquid penetrant in an AC system, it detects where the leak's at. So penetrant inspection is basically used on non-porous metals and non-metal components to find material discontinuities that are open to surface and may not be evident to normal visual inspection. So this part must be clean. If it's not clean, you cannot use it. And of course, this is accomplished by applying a liquid of high penetrating power that enters the surface opening of a discontinuity. Now, the excess penetrant is removed and a developer material is then applied that draws the liquid from the suspected defect to reveal the discontinuity. Now, the penetrant method does not depend upon ferromagnetism like the magnetic particle inspection and the arrangement of the factor. The penetrant method is effective for detecting surface defects in non-magnetic particles. So this is where non-magnetic particles come in handy with this testing, because you get to use it not just on magnetic, but non-magnetic as well. So when you're looking at a surface, so this is going to be the surface. If you're looking at a surface, for instance, there's a crack right in here. Of course, you can't see it because there is something go over here. So if this is my skin and I have a crack right here, you cannot, it's literally in this area right here. To apply this, you would remove it from the surface, you'd remove the surface itself, and apply the actual sealant in there so it actually goes inside there. So it's actually full now. Once the developer is in, it acts as a blotter to draw the penetrant out of the surface and produce a visible indication. So then it's visible now. Now, the different types of systems you can use are fluorescent dye, visible dye, water washable post-emulsifiable liquefolics, solvent, or hydrophilic solvent. Developers, dry powder, and non-water materials. They make it so complicated in here. Non-water materials can be great developers. And then the solvent removers are chlorine and non-chlorinated specifications for class 1 to 3. So to do the process of penetrant, the first thing you're going to do is you're going to pre-clean it. So you're going to clean it beforehand. You're going to let it dry for a little bit. Then you're going to apply the penetrant to it. You're going to apply the solvent, removable penetrant. Then you're going to remove the solvent. Then you're going to let the developer go on it. You're going to inspect it afterwards to make sure the developer is actually on there and it went through. And then you're going to clean and clean out the rest of it. Because once it's clean, then you can use the other parts of it. And there you go. Let me go over it again. You're going to pre-clean it, so you're going to wipe it off. You're going to let it dry for a little bit. You're going to apply the penetrant. You're going to remove the penetrant. You're going to put the developer on over the penetrant to detect. You're going to inspect to make sure it's all good. And then you're going to clean it. And that's the process for dye penetrant. Last but not least is the radiography. Now, the radiography and isotope are similar in some ways. I'm going to skip isotope because it's not very much used in today's aviation field. Same with X-ray because of the safety hazards. But of course, X-ray radiography inspection is an NDI method used to inspect material and components using the concept of differential adsorption of penetrating radiation. So it deals with radiation. So like if you get your X-ray on your bones, it's going to go right through your skin and it's going to detect your bones. So it's just like an X-ray machine except for an airplane. Now, there's different types of scanners for it. Of course, this is how it's used. The radiation is going to come. So I'm going to be the airplane, the part of the airplane. The radiation is going to be this right here. So it's going to be the camera. The camera is shooting the radiation at my face. There's going to be a void area that's over that. So the specimen and the void are actually together as one. You're going to have a film, which is going to actually bring it in. And then you're going to have the black area on the outside, the white area on the inside, the gray area on the middle part. The white is still going to be on the middle part, and the black's going to be on the outside. But this is all after processing. Radiation is in process. The specimen is what it's looking like. The film is what it's on. The black area, the white area, and the gray area are all after processing. That's what comes up with an X-ray. It comes at me. It goes through me, and there we go. It's back on the screen because it's basically it's bouncing back to the visual. It's all visual on this. And that's what's really interesting about radiography. The only bad part about this is it takes a very, very, very long time. It takes a long time to set up, and it can be hazardous to a lot of people. And the FAA requirements, and the OSHA requirements, and the ACO requirements, it's a pretty thick book. It's probably thicker than this itself. So really, a lot of people go over with it. Not really. Do customers mention it? Sometimes. I guess it's not really used that much today because of the safety issues and the cost. So, is it preferable? No, not really. Now, I did forget to mention the ultrasonic inspection. And I'm kind of surprised they don't have this earlier because this is the most important one in my opinion. So you're going to have different types of inspections. You're going to have the pulse echo, which uses a transducer to transmit and receive the ultrasonic pulse. So pulse echo is just like I said, using an ultrasound on a pregnant woman. It's going to go through the actual part of the female, and it's going to pop out with the baby in there. That's just like an airplane. You're going to use the ultrasound to detect a crack down below. You're going to put it over the material, and it's going to bounce inside, and it's going to bounce right back up. Simple as it is. So the equipment of it uses a portable instrument, a frequency range of about 0.5 to 15 microhertz. Transducers, longitudinal and shear waves, positioners, reference standards, and couplants. So that's basically what they're all going to use. The instruments, of course, are a portable battery-powered ultrasonic instrument, and the instrument generates an ultrasonic pulse that detects and amplifies the returning echo, and displays the detected signal on a cathode ray tube or a similar display. Now, I got a chance to actually use the LED screen ones, which is awesome. You literally put it on it, and it bounces back, and it comes up on an LED. Now, excuse me, basically the test specimen, you have the front, the back, and the sides. So basically you have this, you have this. You have different types of scans. You have the A scan, which is going to have the signal amplitude, the front and the back. The C scan, which is just the plain view. And the B scan, which is going to have the amplitude. So really the preferable one is the A scan because it comes with the front, the back, and the signal amplitude, and the flaw. So for instance, you're going to have the signal amplitude. So think of a one of those medical machines that has the little beeps. So if you have one that comes back with one solid, you're good. But then if it comes back a needle and then comes back solid, there's a little bit of a crack in there. It goes up like this, you're fine. But if it goes up 1, 2, 1, 2, 1, 2, that little tiny little one end up being a flaw. So that's when you can detect it, and that's when you can start putting it in, writing it down, and replacing it. So that's basically the main ones that I'm going to go over. The tap testing, I actually really don't know that much about. The geography is not really another big one that I really like to go into, but they're both important. If you'd like to learn more about that, of course, go on the FAA.gov or look at FAA's main downloadable content, which is also on FAA.gov. I want to say thank you guys for checking this out and listening to me. I know this can be kind of dry, but for people that are not really that really don't know about the inspection methods, that they only know about the visual stuff, it's good to teach people about more of the actual materials that are used for it. Because if you just learn how to visually inspect something, it's good. Yes, it's good to know that, but it's also good to know the different types of methods that come into the inspection. I want to thank you guys all for tuning in. I hope that my video went well. Go ahead and subscribe to me so I'm going to post more videos, and go ahead and like. And hope you guys have a great day. If not, I wish you guys have a great day. And also, one last thing, check out Anchor.fm for my other podcast episodes. I'm not sure if I'm going to put this on there yet, but I might. So check it out tonight, and you guys have a great, fantastic night.